everybody. All right. So, I assume everyone saw the email that this current problem set is a 2-week assignment, kind of integrated set of questions over the next 2 weeks. All right. Don't wait in the end. You will really regret it. You will totally regret it if you don't start now. Okay. But as I was mentioning, I think this is really probably the most important problem set of the semester. So pay attention, right? To the ideas and concepts there. All right, so we're talking about this very important fundamental problem, the dynamics of a qubit. And that nicely has a physics interpretation as the physics of a spin 1/2 particle processing in a magnetic field. So if we understand everything there is to know about spins in magnetic fields, we know everything about the dynamics of qubits. So as we discussed, importantly, we're talking about as a 2-level system, a qubit, then a general Hamiltonian will be of this form, okay? Some amount of the identity and some amount of sigma x and some amount of sigma y and some amount of sigma z. That's all there is. And since the identity component doesn't affect the dynamics in any way, because it only affects the overall phase of the state wave function. Of course, it doesn't affect the density matrix. Then we just focus, unless we want, there's other reasons to do so, on this term, which we recognize as equivalent to the dynamics of a magnetic dipole moment proportional to the spin of the particle in some magnetic field, which we generically allow to be time dependent. Okay? And I just want to emphasize one thing here, which can be confusing. This time dependence here, as expressed, has nothing to do with the Heisenberg picture or the Schrodinger picture. It has to do with the fact that we are treating some parameter in the Hamiltonian as explicitly time dependent, which means that we're treating the magnetic field as a classical field, okay, that is parameterized by time. If we wanted to have a full quantum mechanical description of that, we'd have to quantize the B field and then think about what it would mean, as we will in the context of light later in the semester, to think about what it means to be a classical field. We're going to address that a little bit later in the semester. But for the moment, I just wanted to point that out, all right? So in the particular case, if we have a static magnetic field, then the Hamiltonian has this form where we've defined the Larmor frequency in turn as proportional to magnetic field. And if I choose the magnetic field direction to be the z-axis, which we generically would do if we have no other direction in the problem, then the eigenstates are spin up and down along that direction, which is the z direction. And we, by the sign convention, which I snuck in here, spin up is the higher energy state. The spin along the magnetic field is the higher energy state, because I've snuck in that minus sign. Okay. And spin down is the lower energy state separated by h bar omega naught proportional to the strength of the field. Okay? So we were looking then at this incredibly important problem, the problem of spin magnetic resonance, which is really the heart of every quantum logic gate theory, which is thinking about driving the system, in this case between spin up and spin down, with a weak transverse magnetic field, oscillating at some frequency omega near to the resonance frequency. So the idea is that you have your system in a strong magnetic field. We're going to call that the z direction. And then we want to flip spin between up and down by applying some magnetic field transverse to that, oscillating near to the resonance frequency. And the problem we study, we'll finish up, is thinking about a magnetic field that is oscillating, in this case counterclockwise with the right-hand rule, around the z-axis with some frequency omega, and we allow some arbitrary phase at time t equals 0. So our interaction Hamiltonian is the interaction of the spin with that magnetic field, which has this form, right? And I have defined here this frequency, which is the effective Larmor frequency associated with the transverse field, determining the precession around the transverse axis with that frequency omega. So that depends on the strength of the magnetic field, right? The amplitude of the magnetic field determines its frequency, which we call the Rabi frequency. It's not the Rabbi frequency, it's the, he probably was Jewish, it's the Rabi frequency. Anyway, right, so we have these three different frequencies: the Rabi frequency, the resonance frequency, and the frequency of the oscillation of the magnetic field. Keep them straight in your head and remember what each one of them means physically, okay? So our goal now is to solve the Schrödinger equation in this problem, okay? And that is to say we want to find the time evolution of the quantum state in this Hamiltonian, that is a combination of the Hamiltonian associated with the bias field, the static B naught, and the applied transverse field. And to do that, I mean, it's hard to solve that problem in general. In fact, it's generally impossible. This is just one case. It turns out that we can solve it exactly for this rotating magnetic field with the spin 1/2 particle. And the trick to the trade here is to go to the rotating frame. So we go to a frame that's co-rotating with this magnetic field, and in that frame, the magnetic field is static. So we can solve the problem. Okay? So the way we go to do a change of frame in quantum mechanics is to apply a unitary transformation. Okay? And because this is a time-dependent change of frame, there is a fictitious magnetic field that appears in the problem, because this is a non-inertial force, and that's known as Larmor's theorem in classical dynamics. That when you go into a rotating frame, a charged particle sees what is effectively a Lorentz force. That's like the Coriolis force. So this is one of those C forces. So when we did that, then we found that, as expected, the magnetic field is static in the co-rotating frame. And the Hamiltonian in the rotating frame then has the form, wait for it. In the rotating frame, our Hamiltonian has the form minus h bar delta over 2 sigma z plus h bar times the Rabi frequency over 2 cosine phi sigma x plus sine phi sigma y, which this is equivalent to e to the minus I phi sigma plus e to the plus I phi sigma minus, where the detuning is the difference between the applied frequency and the resonance frequency. Okay? So this Hamiltonian has the form of h bar times some total Rabi frequency vector, or Larmor vector, dotted into the vector of Pauli matrices. Right? And this omega tote has a z component, which is proportional to, which is equal to minus the detuning, and then a transverse component whose magnitude is the Rabi frequency and whose direction in the transverse plane depends on the phase. Okay? Why? So this vector has a magnitude which is the generalized Rabi frequency and some direction. So the direction of this field, it's got minus delta in the z direction, and then it's got a component omega over omega tote in the transverse direction that depends on phi. So this is ex cos phi plus dy sin phi. Yes, sir?
By direction, you mean polarization of the magnetic field, or?
I do not mean that. So there are our magnetic field here in the lab frame is this field. That is to say, the part. So we have a in the lab frame, it has a static component in the z-axis and a transverse component which is oscillated. Okay. In the rotating frame, the magnetic field in the rotating frame is equal to the magnetic field in the lab frame minus a component in the z direction, which is this. Okay, so given a certain gyromagnetic ratio, there is a subtracted magnetic field. Okay, so this is the direction. Now I go into the in the rotating frame. This is equal to this b naught. Yeah, it's more complicated now because this is a transform b, right? But the point is this. This is a direction. There's an effective magnetic field here in the rotating frame, which has a component which is way smaller than this, because I subtracted off that huge magnetic field, and then a component that depends on this in the rotating frame. And in the rotating frame, it's that. Okay. I'm sorry? Oh, yes, sorry, omega 2. Yes, thank you very much. So this is what's called the generalized Rabi. All right, so with that said, we can solve the dynamics many different ways, given a Hamiltonian. The simplest thing to do is just to find the time evolution operator here in the rotating frame, as we did at the end of lecture last time. So I just exponentiate the Hamiltonian, and I'm allowed to do that now because this is time independent. I was not allowed to do that before, when it was time dependent. It has the time ordered exponentials. But by going to the co-rotating frame, we made this static. Okay. And this is equal to e to the minus I omega tote t over 2 dotted into sigma, which is an SU2 rotation, as it must be. And you can only have, in a 2D Hilbert space, you're going to have U2, and we got rid of the overall phase, so we got SU2, which is the rotation operator on a spin 1/2 particle. And this has the form cosine of the Rabi frequency times time over 2 times the identity minus I sine omega t over 2 times the direction dotted into sigma. Right? For any rotation on a spin 1/2 particle, my rotation operator has this form. And this, according to what we have over here, is minus omega, delta over omega tote sigma z, blah, 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 minus I e to the minus I phi omega tote sigma plus minus I e to the plus I phi omega tote sigma minus. Oh no, forget about this I. That is out front. That's this minus I. Okay? So, with that said, we now can look at the dynamics of the spin in this magnetic field. So, as we look at the simple case, and I'll do it again, let's just look on resonance first. So right on resonance, we set the applied frequency equal to the resonance frequency, and let's choose the phase to be 0. So in that case, we have in the rotating frame, the time evolution operator is cosine the Rabi frequency over 2 times t times the identity minus I e minus I phi sigma plus sine omega t over 2 sigma plus sigma minus. Right? On resonance, delta equals 0, and I set the phase equal to 0, right? And omega tote. So on resonance, omega tote equals omega. Delta equals 0. Right? So, by the way, this should have said tote times t. Right? Okay, you with me? All right. Some nod, some not, but that's what you do. So, if at time t equals 0, the spin is spin down along the z axis. That's the ground state in the absence of the perturbation. Then at a later time, the state is equal to cosine minus I sine spin up. Right? And so, as we discussed, the probability to be spin up along z as a function of time is the probability amplitude squared is sine squared Rabi frequency t over 2, which is 1 minus cos omega t over 2, which is oscillating sinusoid. And I'll plot this in units of omega t. When omega t is equal to pi, I've gone from, I have a unit probability to be spin up. When it's 2 pi, I'm back down here with 0 probability. And intermediately, I have some possibility that's not either 0 or 1. For example, at pi over 2, I have a 50% probability to be spin up and a 50% probability to be spin down. In fact, at t is equal to pi over 2 omega, that is omega t is equal to pi over 2, then this is equal to spin down minus I spin up along z over root 2, or minus I times up plus I down along z over root 2, which we recognize to be spin up along y. So, if I think about this on the block sphere, if initially the block vector is such that it's spin down along z, that's my state at time t equals 0, then in the rotating frame, the system is precessing about the x-axis, right? So this is where my total Rabi frequency is a vector, it's a torque vector along the x-axis. And the system precesses around that torque vector at a frequency given by the magnitude, which is the Rabi frequency. And when at a time a quarter of a period, it's up here, it's been up along y. At a half a period, or pi, it's been up along z. At 3/4 of a period, or 3 pi over 2, it's been down along y. And then 2 pi later, it's back down. And this sinusoid is just a projection of this block vector onto the z-axis, right? Because the projection onto the z-axis tells us something about and that projection onto that block vector q that we've seen before, rotating around, is just that. This is known as Rabi flopping, or Rabi oscillations. As to say, the system flops up and down between spin down and spin up. Notice, this is coherent. That is to say, the system at all times is a pure state, because it started in a pure state and it evolved according to a unitary transformation, and at all points it was in some superposition of spin up and spin down. In fact, at this point, when this angle was pi over 2, which is known as a pi over 2 pulse, it is in a 50-50 superposition of spin up and spin down. When I do a pi pulse, then I put it all the way to spin up. Okay. Now, a question was asked, a very good question, after a lecture about the time energy uncertainty principle. And how can I get to something? How does that affect my ability to really say I've gone exactly with this frequency from spin up, spin down to spin up? Well, there's a subtle point there. And I refer you to the first problem in your homework assignment to address that problem. Think about that. So what about, let's look at some more general cases. What about when the phase is not equal to 0? Some arbitrary phase. Oh, by the way, as Sam mentioned last lecture, and I want to reemphasize here, all of this is in the rotating frame, okay? Because in the lab frame, this thing is whipping around at the frequency omega of the drive, right? So if I start here, what's really going on is, and eventually it gets up to the top. And that happens way faster. I mean, it's really, it processes at a much slower rate, and it makes that noise before it gets from the bottom to the top. Okay. Sound effects are my new mind. All right. So, all right, good. All right, so we're talking about now when I'm not on resonance, when when I'm on resonance, but the phase is something more general, then the state for that same initial state, the state at a later time, is spin down along z minus I e to the minus phi, spin up along z. Or if I factor out that phase, it's spin up along z plus I e to the I phi, spin down along z. Okay? Yes, sir?
So in this case, why don't we just like re-choose our x and y axes?
It's a good question. Excellent question. So if you're just doing a pulse, then there's no reason to just not set whatever the phase of your oscillator is to call that 0 and define the axis of the Bloch sphere in exactly the same way you did. But if I do two pulses in sequence and I phase shift the second pulse relative to the first, well, then it matters. Let's look at that problem. Before I do this, so let's just play along for a moment. So let's say we've chosen to phase that way because we're done, okay? Because we didn't know better. So this particular state is what? Well, it's a particular superposition that depends on the phase. The phase of the superposition determines what the phase, the phase of the oscillator determines what the phase of the superposition is. Okay. So for example, let's say that this was pi over 2. Okay. Then, of course, I'm going to get rid of that negligible overall phase because we like to have the thing out front of this to be 0 phase. I can always do that. Then this is equal to b over root 2. Of course, it's just being somewhat sloppy, which unfortunately I am from time to time. And that's that. What is that state? Spin down along x. Most excellent. Does that make sense? Is that what you would expect? It should, relative to thinking about what's going on the Bloch sphere. We start with the Bloch vector at the south pole. We haven't bought that from Antarctica yet, so wherever it is. And now we apply a fictitious magnetic field in what direction?
Right here.
So when phi is pi over 2, our torque vector is along y in the rotating frame, right? So this is our torque vector. right? And so I'm going to rotate around the y-axis with the right-hand rule, and I will process with this frequency. So at a time, this is not at a time, this is the time pi over 2 over omega, not an arbitrary time, otherwise I would have the time dependence. I was thinking about this for this particular time. Okay. When I do a pi over 2 rotation and do a pi pulse, this guy rotates and ends up here, which is spin down along y. X. Spin down along x. That's what it is, right? So that makes sense. Now, to readdress your question, Matt, suppose I did a sequence of 2 pulses. The first pulse, I did a pi pulse. Okay, I say a pi over 2 pulse. Now, as you say, might as well set that first pulse to have phase 0. Why said it? There's no reference there, right? So in the first pulse, I've rotated the spin and I've chosen the x-axis in exactly the way that you suggested, and it ended up over here on the block sphere. But now I do a second pulse. And on that second pulse, let's say that I phase shift it by pi over 2 relative to the first pulse. What will happen to this spin? Nothing. It will stay there. Whereas if I did the second pulse not phase shifted, it will rotate and go up here. So the relative phase matters. And that's why as someone in the laboratory, you want to control the phase of your oscillator very well. Because if you don't maintain coherence in your system. It's critical. You also have to have the oscillator. You don't want the frequency drifting around because that's effectively a phase drift. So you've got to have a really good oscillator that is oscillating and ticking away and keeping track of where you are relative to the rotating frame. Because you have a resonance frequency there. It's ticking away, the superposition of up and down, and your oscillator is ticking and keeping track of it such that it looks like nothing happened. All right. So now let's look off resonance. So now we have the general formula over there. And so if I were to ask now, what is the state at a later time? Well, what's that going to be? Well, I have to apply this time evolution operator to the initial state. Again, let's take that to be the south pole. And what am I going to get in that case? I'm going to get cosine omega tot t over 2. And then when sigma z hits it, I'm going to get a minus sign. So I'm going to get a minus I delta over omega tot sine omega tot t over 2 spin down along z. And then I get these terms. This guy does nothing, but this guy gives me a minus I sine omega tot t over 2 e to the minus I phi spin up along z. I missed something, haven't I? I missed this ratio. Have I gotten everything? I think I did. Okay, so now I ask you, what is the probability of finding the spin up along Z at a later time? Yeah, so yeah, as you say, that of course is equal to this probability of amplitude, which is equal to what? And then I have this guy, omega squared over omega total squared. Right? So that's equal to omega squared over the omega squared plus delta squared sine of the square root of omega squared plus delta squared square root over 2. So that's the general formula for an arbitrary tuning for what was called generalized Rabi flopping or Rabi oscillations. Now, what do you notice about that? One thing to notice about this is that there is never, in this case, 100% probability for the spin to be up. What's the maximum probability for it to be up? It's this ratio. The second thing you notice is that the oscillation frequency is bigger. It's bigger by an amount that depends on delta in this form. So if I were to sketch, again, this probability as a function of omega t, what I find is on resonance, I have this, let me sort of try to do that better. We had this sinusoid that went all the way to 1. So that's on resonance. That was for delta equals 0. But for delta bigger than 0, it's either blue or red. It doesn't matter. It only depends on omega delta squared, right? And the maximum that this gets to is the ratio how do you understand that on the block sphere? Well, we have a new torque vector. There's a new torque vector in town. That torque vector now has a fictitious component along the z-axis, right? And so what I have in this case is omega tot has a transverse component and a longitudinal component. That component here is equal to minus delta Ez. Let's say delta is positive in this particular example. Okay. So the torque vector now, for omega, the better omega, is now, looks like that, right? So what happens to the spin? It precesses around this axis with the right-hand rule. And it never precesses such that it gets to the North Pole. Doesn't mean that there's no chance of being the excited state. It just means the probability is never 100%. And the rate at which it does that is bigger by this, length of this vector, which is by good old Pythagoras, omega squared plus delta squared, square root of Pythagoras. And it's just a little bit of geometry to show that the probability, by just projecting this rotating vector on this circle onto this axis, that you get exactly this. Just it's a geometrical problem. Okay. Now, some people like to use some language that I don't particularly like to use, but I'll just mention it. You know, people say, well, you're off resonance, you're not making a real transition. This is a virtual transition into the excited state, and it, somehow that's okay because the time energy uncertainty principle says if I, what the heck are we talking about? I mean, what do those words even mean? We have the Schrodinger equation. The Schrodinger equation tells us how the system evolves a function of time. And this, we started with a system that was not an energy eigenstate, and it evolved accordingly. This is what we see these oscillations to be. All right. Excellent. So, the geometric picture of spins as gyroscopes with torques acting upon them is a powerful picture that allows us to understand the dynamics of any qubit, including our friend the level atom, which we'll get to soon. All right, now we solved this particular problem of the rotating magnetic field as we could. But generically, we might not have an oscillating magnetic field, and as we'll see, for anything other than a true magnetic spin, we can never really get that interaction Hamiltonian ever. So we want to talk about some more generic cases. So beyond the rotating, in particular, let's suppose our magnetic field was just oscillating linearly. Along the x-axis, instead of rotating around the z-axis. So this is just, the problem now here is that I have this static magnetic field, and I apply this going back and forth, very weak transverse magnetic field that's oscillating linearly in time, okay? So, turns out we can't solve that problem exactly. But we can solve it approximately. So let's look at that. The art of physics is the art of approximations. So let's look at our Hamiltonian now. We have in the lab frame, this was the static field, and then we have all right, let's take a closer look. This is my time-dependent magnetic field. At how we might make an approximation to solve this problem. We know that we can solve this problem exactly if we had a field rotating along in some direction, right? However, I can break this field up into two pieces, right? Any linearly oscillating vector that was linearly oscillating along some axis is a superposition of two vectors, one rotating one direction and the other rotating the other direction, right? With frequency omega. Those two circles added together give me a line, right? So I can write this in the tricky-dicky manner as a half of it going plus and a half of it going minus, where this guy is cos, I'll say e plus or minus here, is cos omega t phi dx plus or minus sine omega t dy. Right? So the plus sign was the guy, if this is the z-axis coming out of the board, the plus guy is going around like this, and the minus guy is going around like that. And if I add them together, I add two of the cosines together like that, and the sines subtract. Okay? Now, let's think about what's going on in this relative to the spin. So the spin, in the absence of the transverse magnetic field, wants to precess around the static magnetic field by the right-hand rule. It's going around frequency omega naught. Okay? There is a co-rotating component of this field which is rotating in the same direction as the free Larmor precession. And if this frequency is not so different from this frequency, then the transverse torque, the torque around the transverse axis that is applied, is going to be substantial. And it's going to flip the spin from down to up. In fact, if it was rotating at the same frequency, it would be super substantial, and it would accumulate and would go all the way from down to up. If it's not exactly the same frequency, it's still substantial, but not as substantial, never makes it all the way up. That was the thing I just erased as a bad professor. On the other hand, what about the component that is counter-rotating? How is it going to affect? What is going to be its effect as a torque acting on this spin? Well, I mean, this guy is spinning around like this, and the torque vector, if it's going in the opposite direction. And it's never going to be able to accumulate. It's going to make it wiggle or not. But first it starts torquing, then it torques it the other way. Because it can't stay in phase with this. Is that clear? If this guy is going around the other way, the torque, first it starts torquing like that, and then all of a sudden it finds itself torquing the other way. And it never accumulates very much. And in fact, if it's whipping around so fast, the average effect of the counter-rotating term is completely negligible. If that frequency difference between omega naught and omega is huge compared to the rate of precession due to the transverse. Okay? That, my friends, is known as the rotating wave approximation. So the rotating wave approximation is extremely important. We use it all the time. It's implicit in almost everything that's ever done, although it's not said. So, said another way, let's write this guy as sigma plus plus sigma minus. That's sigma x. And then I'm going to write this as e to the minus I omega t e to the minus phi plus e to the plus I omega t plus phi over 2. So I wrote cosine as e to the plus e to the minus over 2. Is that clear what I did? I wrote cosine as e to the plus this plus e to the minus that over 2. All right? And I wrote sigma x as sigma plus sigma minus. So now, let's go to the rotating frame. This is the frame rotating around the z-axis with the right-hand rule. With frequency omega. So, when I go to the rotating frame, first thing I do is I have the fictitious field, which subtracts off from that, gives me the detuning. And then I get the following. In the rotating frame, sigma plus goes to sigma plus plus sigma minus e to the minus I. And then I have these terms. Oh, this is over 4 now. So notice what happens when I multiply this out. I'm going to get terms where the time dependence cancels. And I'm going to get terms where it adds. The terms where it canceled was related to the co-rotating components. And this is the counter-rotating component. So, if you try to solve the Schrodinger equation in this problem, you're going to have time-dependent coefficients here because we haven't gotten rid of all the time dependence. There is remaining time dependence. However, if we have a separation of time scales, that is to say, if omega and delta are absolutely tiny compared to omega and omega naught, then we can approximately solve this equation. And in fact, we can use fancy methods of ordinary differential equations known as the method of averages to do a controlled approximation. But if we're just loose and sloppy and just say, well, we have fast oscillating terms and they go positive and negative and positive and negative and positive and negative so fast compared to anything else, those rapidly oscillating terms are negligible. But we can make it more rigorous, but we're not going to. Okay? And that, neglecting those highly oscillating terms, when this is true, is known as the rotating wave approximation. Now, most people have forgotten where that term even comes from. What is a rotating wave? But it's about the idea of a rotating magnetic field that was in the original spin magnetic resonance literature. It's long forgotten, except by old people like me. Sometimes we call it the RWA. And again, I want to emphasize the RWA relies on this. Number one, it's a near resonance approximation. You have to be very close to resonance. Your detuning should be small compared to the resonance frequency. The other thing is it's a perturbation expansion. That is to say, the transverse field strength must be very weak compared to your static magnetic field. Or, said another way, your resonance frequency must be huge compared to the driving frequency. Otherwise, you can see that my picture of the rotating field going the other way, it would do a lot if it had a huge torque. Even though it's rotating the other way, it would accumulate. So the rotating wave approximation relies on these separation scales. And as we will see soon enough, in the context of the two-level atom, this is an awesome approximation. We never, ever worry about the breakdown of the rotating wave approximation for laser-driven Rabi oscillations between states. It's just we couldn't do it if we tried to break down the rotating wave approximation. All right, excellent. All right, let's see. What's next? Oh, yeah. So, I want to emphasize here that we have different representations of the state and its dynamics. So, we have one, we can think about, in this case, you think about pure state. We have probability amplitudes. We can write the state and if I don't put a label on it, I mean the standard basis, which is the Z. So I might represent the state in this basis as what's sometimes known as a spinner. It's an old-fashioned language, but it's what Pauli called it. And our Schrödinger equation, I might have a matrix representation. So this is the Schrödinger equation written in terms of the probability amplitudes, where I write a matrix for the Hamiltonian. I'll get rid of my H right there. Let's say on resonance. No, I'm sorry. Phase being 0. Everyone clear that that's the Schrödinger equation in the rotating frame? That's the Hamiltonian, right? Written as a matrix minus delta times sigma z and omega times sigma x. We solved this by exponentiating this matrix. We could also solve it by solving a coupled set of ODEs. And we would get exactly the same equations. Or at least we would get the same solution. Yes, sir?
So this is just for phi equals 0.
That's right. Yeah, otherwise I'd have to have the cosines and the sines in the right spot. All right. So,
I don't see where that came from.
this whole equation?
Yeah.
This equation is the matrix representation of what we wrote down in abstract Rochet notation.
Right. I don't see it yet, because that other one had, you know, E sub A vector, it had
Okay, so this is, so my Hamiltonian,
sigma x, y, and z.
right. So first of all, I'm setting this phase to 0. It had a component like that, right?
Okay, so that's the diagonal.
And then I have plus omega over 2 sigma x. If I had the phase different, it would be in the rotating frame something pointing along that axis. So with the phase equal to 0, it's this. But thank you, I skipped many steps. All right. All right, good. Actually, let's stick with this. I like this. Let's go to the more general case. In that case, what I would have in that case, I would have an e to the minus I phi here and an e to the plus I phi there. Okay. All right. Now, I ask you the following question. So when you're given a Hamiltonian, and you want to find things about the dynamics, you can exponentiate it, as we did, and look at it in terms of SU2 rotation. But a very natural thing to do when you see the Hamiltonian is what? If someone gave you the Hamiltonian, what would be the first thing you would do when thinking about the Hamiltonian? Diagonalize it. You would find its eigenvalues and eigenvectors, right? And of course, I can always express any dynamics in terms of those things once I know it. Okay? What are the eigenvectors and eigenvalues of this Hamiltonian? When you see a 2x2 Hamiltonian, how do you diagonalize it? You look at it always as some effective vector dotted into the Pauli's plus the identity. In this case, there is no identity component, right? This is omega total. So now I ask you again, what are the eigenvalues of this Hamiltonian? Plus minus h bar omega total over 2. Those are the eigenvalues. Right? That is to say, plus or minus h bar over 2, the square root of omega squared plus delta squared. So we expect things to oscillate at the frequency difference associated with the eigenvectors, which is exactly right. Right? Because the dynamics depends on the difference in the energy eigenvalues, which is exactly what we see here. what are the eigenvectors of this Hamiltonian? Spin up and down along what direction? Exactly the direction of this vector. Right? So this guy is, there's a spin up along that axis and a spin down along that axis. And if I know the direction of that axis, then that direction of that axis on the sphere, oh, it's good. Oh, it's good. Yeah. I was going to say this. I was going to have notation connections, but I don't need to. So this thing we said was minus delta over omega tot in the z-axis direction. It's the direction of this guy plus omega over omega tot e perp phi. You had that earlier. This is some direction on the sphere. However, whatever the direction this is. What are its polar angles, theta and phi?
The tangent, phi, is that formula? Omega over omega delta.
Right. So, you know, SOHCAHTOA, did you guys learn about SOHCAHTOA? I don't know. I don't know. But there's, you know, opposite over adjacent for tangent, right? So tangent of theta is omega over minus delta. And phi is phi, the phase of the, that's what my notation conditions are going to be, right? Because this is equal to that direction and the sphere, whatever that phi direction is. So that's to say this thing, this direction E sub A is cosine theta in the z-axis plus sine theta cos phi dx plus sine phi dy, where sine theta over cosine theta is tangent theta, which is exactly what we said before, right? This is the general formula for a unit vector on the sphere with angles theta and phi. So now I ask you again, what are the eigenvectors of my interaction, of my Hamiltonian here? Represented in terms of theta and phi.
Cosine theta over 2 times alpha.
Awesome.
Cosine theta over 2 times alpha.
And then what about this guy? This is where it gets. Did I get this right? Let's see. No. This guy. I always get this one backwards. Let me think about this for a second. I think this is correct. Let's see. These are orthogonal?
Yes.
Yeah. Good. And it works when phi is pi over 2, so that's all here. All right, so now, let us sketch the eigenvalues and think about the eigenvectors as a function of the detuning when I fix all the other parameters. Okay. So firstly, in the absence of the interaction with the transverse field, if I set omega, the Rabi frequency, to be 0, then the eigenvectors are spin up and spin down along Z, and the eigenvalues are plus or minus h bar delta over 2. Okay. So in the absence of the interaction, I have these curves, which looks like this. This is spin down along Z. This curve here is h bar delta over 2. And spin up is that, right? This is the curve minus h bar delta over 2. Is that clear? Those are the eigenvalues and eigenvectors of the system in the absence of the transverse field. Yeah?
I'm confused as to what varying delta would mean in the absence of the field. But
Yeah, this is just a reference point. Okay? So you're right. It's just relative to this frequency, what would those eigenvalues be? But we would never see those. You're absolutely right. But it's just a reference point. Because these are the asymptotes to the problem when the detuning completely dominates, when delta is huge. So now I ask you the question, what do the actual eigenvalues look like? What is this curve as a function of detuning for a fixed omega? These are hyperbola. I'm not being hyperbolic about this, that's what they're called. So, these are the asymptotes of this curve, these curves, when the detuning is huge compared to the Rabi frequency. When the detuning is 0, what are the eigenvalues? Plus or minus h bar omega, the Rabi frequency over 2. Right? And so what we have is curves that look like this. This is what's known as an avoided crossing. That is to say, the two energy levels would cross and become degenerate in the rotating frame in the absence of the interaction. But in the presence of the interaction, that degeneracy is broken. And that generic feature is known as an avoided crossing in the case of any two levels that would cross otherwise. Kind of a word salad, but anyway. So, now I ask you, before we quit here, what are the eigenstates at delta equals 0? In particular, what is the mixing angle? So theta here determines how much superposition I get between up and down, right? It's sometimes known as the mixing angle. It's a horrible term. It should be called the superposing angle, because this is not about a Cisco mixture, but you know, people call it that, so just so you know. It's how much it's really the superposing angle. How much of a probability amplitude do I have of up versus down? So now I ask you, when delta equals 0, what is the mixing angle? Pi over 2. Which means this is cosine pi over 4, and this is sine pi over 4, which is 1 over root 2. So what I have in that case is an equal superposition of spin up and spin down, but with a phase that's determined by the phase of the driving field, relative to whatever I call 0 to begin with. When the phase is 0, it's a symmetric and antisymmetric superposition of those two states. So now I just want to conclude with the following statement. Notice how the nature of the eigenvector, if you can read my sloppy handwriting, I'm sorry, as a function of the detuning. If I'm all the way to the red here, the ground state is spin down. Okay? Now as I sweep the detuning, the nature of the ground state is changing. Right here at 0 detuning, the ground state is a 50-50 superposition of spin up and spin down with particular sign and phase that depended on the phase of the applied field. And as I continue to sweep through resonance to the blue side, all of a sudden I come up on the other side, spin up. We're going to have a problem about this in homework. This is known as adiabatic passage. It's another way to flip a spin from spin down to spin up. This, as you may have learned in your quantum mechanics classes, is an example of the adiabatic evolution of the system. If you change, in this case, I make that detuning an explicit function of time. And if I change that detuning slowly enough, and what slowly enough means we'll think about if we haven't thought about it in the past, then the system doesn't Rabi oscillate between those states. It will stay in the local ground state. What Rabi oscillations correspond to is the sudden approximation, as he suddenly raises his voice. Sudden means I just turn on the field out of nowhere so quickly, and all of a sudden the system finds itself in a superposition of two states, and it will oscillate between them. So one has to think about when one's turning on the laser, are you doing it fast or slow? We'll come back to that in a little while. All right. Have a good afternoon.